Special theory of relativity. Albert Einstein's one of the greatest scientists in the world. In 1905 he discovered the theory of special relativity is one of the most important papers ever published in the field of physics. Special relativity is an explanation of how speed affects mass, time and space. The theory includes a way for the speed of light to define the relationship between energy and matter. Small amounts of mass, m, can be interchangeable with enormous amounts of energy, E, as defined by the classic equation E equals mc². Special relativity applies to special cases. It's mostly used when discussing huge energies, ultrafast speeds, and astronomical distances, all without the complications of gravity. Einstein officially added gravity to his theories in 1915, with the publication of his paper on general relativity. As an object approaches the speed of light, the object's mass becomes infinite and so does the energy required to move it. That means it is impossible for any matter to go faster than light travels. This cosmic speed limit inspires new realms of physics and science fiction, as people consider travel across vast distances. What was physics like before relativity? Before Einstein, astronomers, for the most part, understood the universe in terms of three laws of motion presented by Isaac Newton in 1686. These three laws are: objects in motion or at rest remain in the same state unless an external force imposes change. This is also known as the concept of inertia. The force acting on an object is equal to the mass of the object multiplied by its acceleration. In other words, you can calculate how much force it takes to move objects with various masses at different speeds. For every action, there is an equal and opposite reaction. Newton's laws proved valid in nearly every application in physics, according to Encyclopaedia Britannica. They formed the basis for our understanding of mechanics and gravity. But some things couldn't be explained by Newton's work, for example, light. To shoehorn the odd behavior of light into Newton's framework for physics, scientists in the 1800s supposed that light must be transmitted through some medium, which they called the luminiferous ether. That hypothetical ether had to be rigid enough to transfer light waves like a guitar string vibrates with sound, but also completely undetectable in the movements of planets and stars. That was a tall order. Researchers set about trying to detect that mysterious ether, hoping to understand it better. In 1887, wrote astrophysicist Ethan Siegel in the Forbes Science blog, "Starts with a bang." Physicist Albert A. Michelson and chemist Edward Morley calculated how Earth's motion through the ether affected how the speed of light is measured, and unexpectedly found that the speed of light is the same no matter what Earth's motion is. If the speed of light didn't change despite the Earth's movement through the ether, they concluded, there must be no such thing as ether to begin with. Light in space moved through a vacuum. That meant it couldn't be explained by classical mechanics. What does E equals mc² mean? One of the most famous and well-known equations in all of human history, E equals mc², translates to energy is equal to mass times the speed of light squared. In other words, energy, E, and mass, m, are interchangeable. They are, in fact, just different forms of the same thing. But they're not easily exchanged. Because the speed of light is already an enormous number, and the equation demands that it be multiplied by itself, or squared, to become even larger, a small amount of mass contains a huge amount of energy. For example, PBS Nova explained, if you could turn every one of the atoms in a paper clip into pure energy, leaving no mass whatsoever, the paper clip would yield the equivalent energy of 18 kilotons of TNT. That's roughly the size of the bomb that destroyed Hiroshima in 1945.